But tonight's speaker, Ken Caldeira, has had a long career of thinking about systems that can surprise us. Ken is a senior scientist at the Carnegie Institution's Department of Global Ecology, which is located on Stanford's campus. He's also a professor at Stanford, where he teaches in the Department of Earth Systems Science. Ken explores a wide range of questions about climate systems, from the global carbon cycle, to oceanography, to the long-term evolution of climate, to climate intervention proposals and energy technology. Like all Carnegie scientists around the nation, there's a number of Carnegie labs. Ken's job is to, quote, make important scientific discoveries. That is a great job to have. I was a postdoc at a Carnegie lab, and yeah, it was one of the best times of my life scientifically. The Carnegie Institution offers adequate base-level support, so Carnegie scientists are free to work on the questions, the problems that they think are the most important without worrying about having to write that very next grant proposal to keep the lab running. And it lets them take risks that other scientists might not be able to take, and to work on problems that take longer to germinate. Ken recently served on a committee formed by the US National Science Foundation that produced a 2015 report early in 2015 on climate interventions, and he's served on other high-level international panels. From the early 1990s to 2005, Ken was on the research staff at Lawrence Livermore National Laboratory, where he was awarded the Edward Teller Fellowship in 2004. That's the highest award given by the laboratory. Ken did his postdoctoral research in geosciences at Penn State and at Livermore. He received his BA in philosophy from Rutgers and his MS and PhD in atmospheric sciences from NYU. And in the 80s, Ken held a number of positions developing computer software for clients in the New York financial district. So among Ken's many key contributions are his early recognition of the threats that are posed by ocean acidification, his pioneering investigations into the environmental consequences of intentionally intervening in the climate system, or geoengineering, and helping us to understand what long-term geochemical cycles, which play out over hundreds of thousands to millions of years, what those long-term cycles imply for the fate of today's carbon dioxide emissions. So please join me in welcoming Ken Caldeira.
Thank you, Paul, for that very nice introduction. And let me thank you all for coming tonight, because I know you're all busy people and your time is valuable, and hopefully I'll help you to use your time wisely this evening. There's no refunds. So, given that this is a conference about climate science and climate and policy, I thought that would be a fitting title for this talk. And so, basically, I'm one of those scientists who have been foolish enough to interact with the media and the policy process. And so part of the first part of the talk will be sort of telling some war stories of just things that happen when scientists try to communicate in public. And then we had a paper come out in Nature this week, and so for a few minutes I'd like to actually do some science and show some of the science that I do, just so you know that I'm not completely a charlatan. So I thought I would actually frame some of this around talking about around like what I did this week. And so one of the things I did this week, that there was a meeting at UCLA, and about this issue of is it possible to power, is it a good program to try to power civilization with 100% renewable energy system? So just basically, so one of the people here is Mark Jacobson, and he's proposed that we should try to power the Earth using only wind power, solar power, and hydropower. And then this is Dale Brick from NRDC, who is involved from a political, NGO kind of way of trying to transform our energy system. And then you have Michael Schellenberger, who helped form the Breakthrough Institute and has his own sort of pro-nuclear think tank. And then there's me. And then the other person here is Oliver Morton, who is our moderator, and he's written a book recently on geoengineering, and we'll get to that a bit later. But the first question is, like, I was trained as an atmospheric scientist. I do some ocean acidification field work and other things, and some computer simulations. What am I doing up there talking about energy system transitions? And I have co-authored papers that take, a high-level bird's eye view of the planet and maps out, how much energy are we using and what are we getting out of different sources today. But in terms of engineering of real power plants, I'm basically an ignoramus, and so what am I doing up there? And so I'll just go to the next slide just so you don't have to stare at all those people while I'm talking. So what's the question one of the things that social science has been finding recently, and this is kind of a theme I'll come to at the end, is that, how do people change their minds? And the social science is saying that just, getting somebody throwing facts on you doesn't lead people to change their minds very well. And, we see this, say, in the Republican campaign. It's probably a good illustration of this. But and so there's all this tribalism and words, relate to tribalism. And so we have this idea that renewable means good. And everybody likes renewable energy, and it sounds good. When I first came into doing science in the 1980s, I know that I thought, basically wind, solar, maybe biomass sounded really wonderful. And then you start, looking at how do you actually power a civilization using only, say, wind, solar, and hydropower. And the problem is that the wind blows when the wind blows and the sun shines when the sun shines. And there's really not that much room for expanding hydro. And, so what do you do when the wind's not blowing and the sun's not shining and you still want electricity? And, it turns out that chemical batteries are expensive, and you can do things with pump storage, but it's really hard to site pump storage things. There's some ways to do thermal storage, but that tends to be expensive. So what I was doing in that meeting, since I'm not a energy sort of engineering expert, is saying, well, look, that if you keep the portfolio open, that that gives you more options, and so that if you can't do your pumped hydro station, maybe you can do a gas plant with carbon capture and storage, or who knows what, and that having more options will not only make things cheaper and easier to solve, but also lets you build stronger political coalitions. Because if you say you're just going to do things with wind, solar, and hydro, wind, solar and hydro, then you're telling the agricultural industry that they have no future role in any future energy system, the nuclear, the fossil fuel, and you create all this political opposition. So anyway, so there's this mix of like my own political views and semi-informed views on energy systems, and you find yourself in a debate with all these people. So, So that Michael Schellenberger, who I pointed to, this guy over here this is Jim Hansen, who's probably one of the most famous climate scientists in the world. This is Tom Wigley, this is Carrie Emanuel, and that's me. And what does this say here as it's fading out? It says, climate scientist pro-nuclear. How did I wind up, this is at COP21 in December. What am I doing there? Who know almost nothing about nuclear power. I was arrested protesting at Shoreham. What am I doing there? And so what happened was, there was a letter that I don't know who originally started the letter, but Tom Wigley sent me this letter. Tom Wigley, I know he was a friend of my PhD advisor, and I've known him for a long time. And he says, "Oh, Ken, we're going to sign this letter." And I was working at the president of Carnegie Institution at the time, was a former chairperson of the NRC, Nuclear Regulatory Commission. So I sent him the letter and I said, look, and he thought that it was too gung-ho nuclear. And so he kind of like got rid of language that he thought was bad. And then there's a guy at Berkeley, Per Peterson, who's a nuclear expert. So I said, I showed him the letter and he sort of cleaned it up thinking it was too gung-ho. And so then once those guys thought it was all right, I signed it, thinking like, okay, I'll sign one letter, it will go somewhere, and I'll never see it or hear from it again, and I'll make Tom happy and get him from bugging me to sign something. So, the next thing the letter's out there, you're getting calls from journalists, so this thing of COP21, I was like, look, I don't want to go to COP21, I'd rather stay in my office and do work. And I don't want to fly all the way to Paris, and deal with crowds and jet lag and everything. But they convinced me, they said, look, if you don't go, then they're going to ask you, journalists are going to come to you and ask you why you didn't go. And then, like, did you change your position? Are you against these guys? And so anyway, so they convinced me, like, the least troubled path is for me just to go. And so I went and did this thing, and again, I'm not really arguing. These guys are pro-nuclear. I'm just for keeping an open portfolio and let's let things compete and let's have appropriate regulations and things like that, but let's not prejudge everything. And so anyway, I went through that, survived that. Okay, so then I'm on Lou Dobbs' show, right? So this is Fox Business News. There's a snowstorm in the east, and they want to find a climate scientist that they can whack and say, "Where's your global warming now? We're in the middle of a snowstorm." So I'm foolish enough to do this because I'm enough of an egomaniac that I'm willing to put up with Lou Dobbs to get on TV. So first of all, there's a couple of things. We're in the middle of this thing in a snowstorm, and he starts asking me about nuclear power. And I'm like, oh my God, I was expecting to get lambasted for believing in global warming. And here I am on nationwide TV being asked questions about nuclear power, of which I know almost nothing. And I just thought, like, if you want somebody to talk to somebody about nuclear power, please get somebody else. So from this time, I've learned just to be more careful in what letters you sign and sort of think it through a little more, even if you actually agree with everything. And there's a thing that, as a climate scientist and as somebody who dabbles in big picture energy systems, that people don't know when you're an expert and when you're not an expert. And so if somebody talks to me about ocean chemistry or maybe feedbacks in long-term carbon cycle, I can have some professional expertise I can bring to that. If somebody asks me, what do I think about Edward Snowden? I can tell you what I think about Edward Snowden, but nobody thinks that me being a climate scientist gives me any special right to comment on Edward Snowden. But when it comes to nuclear power, that's like close enough to climate science that people aren't sure, like, does this guy know what he's talking about, or is he just babbling? And for me, I don't want to do too extreme, but I think I know something about big picture global energy systems, but in terms of, engineering particular plants. And so, for example, there's now some people who are trying to save Diablo Canyon plant, which might be closed down, and they asked me, would I sign some letter to support Diablo Canyon? I said, look, I don't know anything about this particular power plant. Count me out of that one. So this shows that there is learning. But the one thing that was good about Lou Dobbs was, and this is that we were in separate studios. And I remember when I was, that some people were saying, that when you're on these kind of shows, that they have the advantage because they can kind of see you and they're professionals and you're coming in there, you know, you didn't get any makeup, you forgot to do anything with your hair or anything. And, you know, they're all like knowing what they're doing. But what actually was that I didn't get to even see his face or anything, which actually made it easier. Because if somebody's in front of you, you wouldn't like make fun of them. But like some of his questions, I just started like laughing at him. And it actually worked out reasonably well. But again, I didn't want to be asked about nuclear power. So, you know, as Alan Robach knows, you know, so one of the things we did, we were at I'm not sure, were you at the 1998 meeting with, when Lowell was there in Aspen, that one? So, okay, anyway, there was a meeting in 1998 in Aspen about how to solve the climate problem, and Lowell Wood was there, who was a protege of Edward Teller. And, you know, he said, oh, you want to solve the climate problem? Well, one way you could do it is you could just have a nuclear war. Might create another climate problem, as Alan Robach is well aware. But then he said, well, we could also just reflect sunlight away from the Earth. If greenhouse gases warm the Earth, we could reflect sunlight away from the Earth. And we were working at the same lab, both at Lawrence Livermore National Lab, but I had never met him before because there were 7,000 people working there. And my friend and colleague in the next room was Bal Govindasamy, and he was running atmospheric models. And so we said, oh, let's try turning down the sun, deflect some sunlight away from the Earth and see how the climate works. And so we started doing those simulations and did a series of simulations after that. And, you know, and some people got the idea that I was commanding a fleet of airplanes, and that when you look outside and you see contrails behind the planes, that's me doing that. And I think I'm in cahoots with David Keith doing that. And they'll clip that thing that I just said. I'm in cahoots with David Keith doing that. Take that clip and put it on YouTube. So that's probably going to be there. And so one of the things I learned is you have to be, here's an example. I was at some meeting, and there was a discussion in public, and it's getting more and more like that, things are streamed and live forever. I learned the hard way, you can't say I or we. Like you say we, and I'm meaning we, humanity, we're all together. You know, people, you say we, and people hear you, white, older, technocratic men. And anyway, so it's just a tough thing, you can't say we. So anyway, there was a discussion, which was a serious moral discussion, and this was about, Katrina, you know, if there was a mechanism, so Katrina, you know, went into New Orleans and 2,000 people died. If it would have been possible to steer Katrina somewhere else and 5 people would have been killed, you know, would you steer it and avoid 2,000 deaths, but you would cause 5 deaths? So this is a moral question. And I learned you have to talk about that in the abstract, you know, because if you say, I don't even want to say it here because they'll clip it out again and it'll be on the thing. But if you used a personal pronoun, first person personal pronoun, and said that pronoun would do this decision, you know, then you get this thing on the thing saying, oh, that this personal pronoun's willing to kill 5 people, he's obviously evil, and he must be commanding a fleet of airplanes that's poisoning our skies. So, yeah, so one of the things is, as scientists, we're not trained for public communication. We're not trained, you know, we're trained to sit in our offices in front of laptops and type and stare at screens and make figures and write text around them. Try to get it through the peer review process. Okay, so let me now switch to that other piece that involves writing text and making figures in the peer review process. So I'll go to do a little bit of science now, and then I'll come back to more general policy stuff in a second. So when I was a graduate student, there's Jim Zakos over here, and he was at Rhode Island, and he was taking carbon isotopes at the end of the Cretaceous mass extinction event, and showing, which indicated how ocean productivity varied, and plankton play an important role in the carbon cycle for many reasons, but one of the reasons, first of all, they pump carbon from the surface ocean to the deep ocean. They also form calcium carbonate shells that are the ultimate repository for CO2 that's coming out of volcanoes. And at the end of the Cretaceous, when the dinosaur, maybe you could say what it was, but probably an asteroid or something hit the planet north of Yucatan Peninsula and wiped out the dinosaurs. And for my dissertation work, I tried to model the data that Jim was collecting. And there was another guy, Brad Updike at University of Michigan, who was looking at controls on carbonate mineral accumulation in shallow water environments, which today are things like coral reefs. And I don't want to go into too much detail, but the basic point was that something apparently stabilized the chemistry of the ocean at this time. And what I hypothesized as putting this work together was that the production of calcium carbonate shells and their burial in the shallow water coastal environment must be very sensitive to ocean chemistry, because that would explain why the ocean chemistry didn't go more crazy at this extinction event. And so this was seen as a sort of just purely theoretical thing. I think I had a paper in paleoceanography. I think for the next decade after that appeared, I think every citation was a self-citation. You gotta do what you gotta do. You gotta get that H index up there. But this thing about that the shallow water, these corals and so on, were very sensitive to changes in ocean chemistry. In the late 90s, people like Joni Kleypas from National Center for Atmospheric Research started noticing, that ocean chemistry was changing, and that this, pointing out that this would have make a big problem for corals. And so we did some other work, but mostly at that point I was purely a modeler and didn't do any field work. And so don't let this frighten you here, but this is a measure of the kind of chemical potential or the chemical force that's helping corals to produce their skeletons. And so aragonite is the name of the mineral that the skeleton is made out of. And this is the amount of CO2 in the atmosphere in these simulations. So in pre-industrial, so this is what the chemistry of the surface ocean looked like pre-industrially. And basically you see that almost all the corals were living near open ocean water where this chemical force helping them to build their shells was greater than 3.5 or so. And all of them were in waters surrounded by open ocean waters greater than 3. If we march this forward in time, this is about what it was more or less in 2005 or so. We're up to around 400 now. But you can see just going from pre-industrially to early 21st century, a bunch of corals are probably moved into kind of an unsustainable state already. And as this goes up, this is sort of like a mid-century under business as usual. And this is sort of end of century under business as usual. And there's basically no place left in the ocean with the kind of chemistry that supported coral reef growth through much of Earth's history, or at least through the last tens of millions of years of it. And so the basic conclusion of this work is, well, yes, there might be some adaptation, but you have to think that even back when it was like this, at the edge of this range, the corals were trying to spread out to occupy more territory, and they were unsuccessful. And there's questions, well, there's light limitation and temperature and all these other things, and this is where paleo evidence is really important, because we can go to warm periods in Earth history and ask if the corals spread out to broader latitudes, and it looks like occasionally they did, but not too much. And so it looks like really this chemical control is a major control of coral distribution. And if that's true, and we continue doing what we're doing today, there'll basically be no place left in the oceans where corals will be sustainable. So, yeah, before I go into this picture, let me first back up a little bit. So in the introduction, it was mentioned that I used to work in the financial district in New York. Yeah, so what do you do when you graduate with a philosophy degree? And, luckily, my high school was one of the first high schools to get a time-sharing computer. I remember we had 8 people time-sharing after 64 kilobytes of RAM and paper tapes and things like this. And so I had learned computer programming in high school and kept it up as sort of a hobby through college. And so I graduated and, oh my God, I've got a philosophy degree. What am I going to do? And so the only thing I knew how to do that somebody would pay me for, other than like picking fruit or something, was doing computer programming. So I got a job doing some tech place, and then another job, and then another job. And I ended up in the financial district. I worked for banks and New York Stock Exchange, looking for insider traders and things like this. But basically, the job was micro interesting and macro meaningless. That it was, because it was like interesting little things, but you're basically working to make rich people even richer, and it just wasn't very meaningful. So, but luckily, what I would do is I became a contract developer. So I would get a contract and work for 3 or 6 months for somebody, and then go off somewhere else. And so on one of these goings-offs, I was a field assistant for some ecologists in the Mexican rainforest. And I thought, oh, well, this is really cool. And I thought, but if I ever want to lead an expedition to the rainforest, I'm going to have to get a PhD, because they're not going to just let a philosophy major do it. So, and the other thing, so the other thing, which I don't have a slide for, was in 1979, which I'm showing my age, I know this, but in 1979 there was an article in the New York Times, and Steve Schneider had spoken at a AAAS conference saying that global warming could melt the West Antarctic ice sheet. And just this idea that our emissions could melt an ice sheet seemed so startling to me that it just seemed like something I should get involved in. So between this thing of doing this field work and then reading that article in the New York Times, I thought, okay, climate science is good. And so, and then also it turns out that Marty Hoffert and them were only 8 blocks away from where I lived, and I could start going at night school and stuff like that. So anyway, but the thing is this, you're a computer programmer, and they don't send you to the rainforest right away. They say, oh, here we have some cheap labor, and you can do some computer modeling for us and stuff like this. And so, they stick me behind a laptop, or that time it wasn't a laptop, it was a desktop with a big CRT screen, and there I am with my ambition to get to the rainforest, and I'm once again staring at a computer screen. And so it wasn't until I got to Carnegie about a decade ago that I met with Jonathan Erez from Hebrew University and talked to him about possible field work, because I started feeling like the modeling stuff on the ocean side was reaching its end. And so I hired a couple of his graduate students, and we started doing field work maybe 7 years ago in Australia at a few places. But one of the places we did field work in, and the place we've done the most field work is this place called One Tree Island. And that's One Tree Island there. It actually has more than one tree. But this is a really interesting, it's pretty much at the southern end of the Great Barrier Reef. And this reef is really interesting because it's called a ponded reef. And at low tide, the water level here is higher than the water level there. And so it acts like a bathtub and holds the water in. And in certain places, the water flows over the reef crest. And this became really important for the experiment I'm about to describe. And we did a number of just observational experiments there. And one of the problems is, in the real world, first of all, there's obviously all this variability, but nature doesn't, just reveal all her secrets to you. If you're trying to understand controls on the growth of how fast the corals grow their skeletons, that the times the light is strong is the time they're photosynthesizing fast, and then they're also growing their skeletons fast because they have this energy to grow their skeletons, but then that alters the water chemistry, and so it turns out that light, growth rate, water chemistry are all correlated, and if you try to just plot one against another, they all show some statistically significant trend, but most of them are causally meaningless. And so how do you separate, how do you get beyond correlation to causality? And so we thought, okay, well, if we want to we need to uncorrelate the chemistry changes from everything else and isolate what's the effect of chemistry changes on the corals. And this is a similar thing. So it's been observed that these corals are growing slower over the last few centuries, but how much of that is due to overfishing, how much of it's due to coastal pollution, how much of it's due to warming, how much it's due to ocean acidification. And so we tried doing an experiment so this rim right here, let me show you where it is there. Oops, I pushed a button there, I pushed another button. That rim that picture is like right here. So looking that way. So, and so this water, remember, is pouring out here at low tide. And, so what we did is we made a tank, 15 cubic meters, filled it with highly alkaline water, which is basically an antacid, and then pumped this water onto the reef as it was flowing across, tried to measure the difference in chemistry between here and there, and estimate how this change in chemistry affected reef growth. And one of the things I have to say, we tried this experiment 3 times. Each time it took a team of 10 people out there for 7 weeks. And we've sort of done this over a 5-year period. And this thing about this base funding from Carnegie is really important because in today's funding situation, scientists aren't allowed to fail anymore. And failure is really important to the progress of science, because if you do only things you know are going to work, that means that these are just going to be taking these little baby steps and not doing it. And if you did an NSF proposal and you got funded and it's some 2-year funding horizon, you say, okay, we did the first expedition, it failed, give us more money. And then, okay, we tried it again, it failed again, give us more money. And then, that you'll never get funded for it. And so I'm really fortunate being at an institution that has some base funding, thank you, Andrew Carnegie. But each time you fail, you learn something from it. And we got some papers out of it, and so I didn't declare to my department, hey, we just failed, but our main experiment didn't fail. An alarm? Okay. Okay, so this is now the other side of it. So these two, actually, if we put these two together, so this is sort of pumping the water on there. This is this dye thing. So there's also this pink rhodamine dye there, and then this is our sampling team sampling at the other side. And this whole, I'm not going to have time to go into all the details, but the natural system is so variable. It was this whole signal to noise issue, because how do you know what's just natural variability and what's your treatment? And we're trying to measure an amount of change that's equivalent to 1 gram of calcium carbonate over an area like 30 meters by 40 meters. So I don't know, something like, I don't know the exact size, but something like this middle, maybe a little bigger than this middle piece of seats here, and we're looking over the course of an hour, maybe trying to find 2 ounces different in a very variable natural system, and so we're pushing all our equipment to the edge of detectability, and we're trying to reduce every degree of uncertainty. So this last time we did, to reduce uncertainty, we nailed bottle caps into dead coral at the bottom so that our sampling location was always within a centimeter of where we sampled it the other day, because there can be like a little, oops, I keep doing, there could be a little, the water could flow under the coral or over the coral, and if you sample that water, it's completely different chemistry, and it might be just 10 centimeters away from the other one. So anyway, you don't need to hear all this kind of stuff. But so this is just this picture of, that was our study area. This is this idea that the water's going over at low tide, and then we had these plumes and these two transects that we're looking at trying to do the change in the relationships between our dye and what's called alkalinity across these things. And we're trying to show that the reef's taking up some of our alkalinity. And so now, I don't want to go through all this kind of stuff, but basically we measured all these points along the front line and the back line. And so this difference in concentrations here represent the reef picking up more. This is the reef taking, building calcium carbonate, taking chemicals from the ocean to build its skeletons. If it didn't respond to our addition of material, this slope of this line of the dye versus alkalinity would be the same. So we were trying to detect that the amount of growth was bigger where we added the antacid, and indeed that's what we found. And so we did this over 22 days, and said this is just the amount of total alkalinity uptake, how fast the reef was growing, and then this was what fraction of the dye that we added got taken up each day, and it was typically something like 17%. And so this is the slopes, and if you take the means of what I just showed you for the control days and experiments. And so, so we concluded that as a result of our treatment, that the reversing the acidification to the extent we did it increased the growth rate by 7%. We didn't really our goal was to bring it all the way back to pre-industrial times. We only brought it part way there. And so we estimate that if you did bring the chemistry all the way back to what it was a few hundred years ago, the reef would have been growing 12% faster. So at least at this location, there was a 12% reduction, likely a reduction of around 12%. Of course, there's all issues of acclimation and everything else. I don't want to get into all the caveats right here. But so anyway, after 5 years, we got this into Nature, and then this was just yesterday on the Nature website in their news thing of it, they call it Landmark Experiment Confirms. And so we were, we felt like, oh man, we put all this effort, at least people are saying nice things. So anyway, that was just a little success story. This just came out in yesterday's Nature, so we were very happy with that. So that was actual science. So now, what's the point? You're probably wondering, like my talk, what's the point here? So, so this is back to this model of social change. I started out this thinking like, if we only had good information and we got that to the right people, they would make good decisions and the world would be a better place. And, the sad thing is that, now it seems a lot like there's a lot of sort of tribalism and that, that's all this sort of cognitive, is it consonant with my belief set? If it is, I saw this one video once of they hypnotized a guy and told him that his friend wasn't in the room. And they go sit in that chair over there. And his friend was sitting in the chair. And the guy's doing everything to avoid looking at the chair because he doesn't want information that goes against his belief set. And then he's saying, I've been sitting all day, I feel like standing. And and I think like we're all going through life hypnotized and refusing to acknowledge things that aren't cohering with the rest of our belief set, and that just giving, so this guy had the information entering his brain that his friend was sitting in the chair, but he wouldn't let his conscious mind process that and deal with it appropriately. And so, this question of how to do this science policy interface in a way that transcends these kind of tribal barriers is a tough one. So I'm on the board of this organization. It's a small little thing that's just starting, but it's called Near Zero. And the idea is it's just public information to try to get good science information into the public policy process on mostly on energy technology type issues. And the original thing, the way this started out was we had this model of social change, like we're going to get good information to policymakers and they'll make good decisions. And we were talking to one staffer at the Senate Energy Committee. So we do some work, helping to keep Bill Gates informed sometimes. And so we thought like, oh, what if Bill Gates would fund an intern for every senator and every representative who knows about energy issues? Would that help? And the staffer said, well, they would kind of look at that as a waste of space, that they don't have that much office space. Now, if you could get them somebody that would help them in their campaign fundraising, that they would like. And, it's just, and so now we're in this little, at least maybe other people sort of have a sense of purpose. I'm like in this existential dilemma of like, what are we doing? Like, how do we bridge this science policy barrier? And so, there are some hopeful signs. It's not completely depressing. One thing as a result, partially as a result of our seminar series and getting good information to at least Bill Gates, of course, he has other sources of information, that he went and pushed for a doubling of R&D budgets for publicly funded clean energy R&D, and also is trying to put together a private fund for clean energy commercialization, and so at least there's some movement. In some cases, information helps. So what time is it? We're coming towards the end here. So let me I'm not going to go through that one. I'm going to go through this one. When I sent this in, they said, are you sure you want to show that? Like, is that a mistake? But this was Sarah, who was organizing, I don't know where she's sitting here, but she was organizing this. And it was like, what the title, aren't you going to tell us what you're going to talk about? January 22nd. I did it well ahead of time. I don't know who was complaining about me being late. So what did I say? I would probably first discuss some of our own research results. I didn't do that first, I did that later. I was going to show other things besides the ocean acidification, but that was enough. I also do climate modeling. Yeah, I'd like to mention that while the questions that we ask and what we do with the answers reflect values, biases, motivations, etc., as scientists, we should aim to provide objective answers to empirical questions. I didn't say that. Yeah, so this is one of the things that, like, I remember the first time I went to testify in Congress about ocean acidification. They said, oh, well, what do you think we should do? And I was there saying, well, look, I'm here as a scientist. I don't tell you about what we should do. I tell you what the facts are. And I tell you empirical facts, and you policy people use that information to make good policy. And they were like, no, we don't want you just to tell you. We wanted to know your opinion of what it is. So I said, oh, you should give more money for ocean acidification research. And then after that, they go, oh, that's good. Okay, thank you again. So then I get off, and then the staffer comes up to me at the end of it. It goes, well, of course we're not going to increase the budgets for marine sciences. So what part of marine sciences should that money come from? So, yeah, I'm likely close by discussing the issue related to scientists opining on topics outside of their expertise. This is where I started. The thing is that you're a climate scientist, and one day somebody will ask you about the ice sheet. What do you think of the ice sheet? What do you think of the thermal helium circulation? What do you think of the permafrost? What do you think of Arctic sea ice? What do you think about the threat to food security? What do you think about extreme events? Do you think Katrina was a cause for this? And no climate scientist is an expert on all this stuff. And so anytime a scientist enters the public domain, you're getting asked all these questions of which you're not an expert about it. And so do you just say, but you probably know more about it than the next person. And so this question, even within science, you always have this question of, should I stick narrowly to where I am actually an expert? Or a lot of these things, I have a friend who studies ice sheets, and my friend told me this. And so when the journalist asks me, I'll tell them what my friend told me, and then they'll think I'm an expert on ice sheets. I've even been a co-author on a paper on ice sheets, but I know nothing about ice sheets. but I know what my friends tell me, and I repeat that to journalists. Okay, maybe that's a good place to stop. That's my lack of expertise exhibited.
They're going to set us up.
That's the person to whom this email is addressed.
Yes,
right?
Sarah.
Sarah. I can put this one up just for jollies.
Really? Oh, thanks a lot. Uh-oh. Small text. Oh, thanks a lot.
I should sit here?
Yeah, oh, yes, please. We will sit and talk. Okay. I'm gonna ask you some questions.
Okay. Oh.
And
is this like conversational?
well, we'll see, because I know even less about these topics than you. So okay. I need to take my glasses off so I can see. So
do you want me to tell you which ones I actually know about, or when I answer? How about if I answer and you tell me whether you think I actually know about?
Okay. This one is topical for us in California. How much impact on global warming does methane have compared to CO2? And please comment on the conversion of methane into CO2.
Maybe you know it better than me. I forget what the radiative force thing. I would go to what I would do normally in these circumstances is I would quickly Google the IPCC report and see what they said in the IPCC report and find it there. And so I don't have the exact numbers, but methane's less than CO2, but it's substantial. The main difference is that methane, the concentration perturbation for methane lasts around 12 years or so, whereas so methane's a potent greenhouse gas, but short-lived. CO2, some CO2 hangs around for many thousands of years. And that actually, as paleoclimatologists know, that more energy is absorbed because of the long lifetime of the CO2 after the methane oxidizes, more is absorbed by the CO2. That was probably too long an answer to say, I sort of halfway know something relevant about that one. Yeah. But not the exact answer.
So this is my father, Hans Suess, and his colleague Roger Revelle.
Somebody raised their hand. Your dad is Hans Suess. That's, I guess it's not an accomplishment, really. It's just
we're very concerned about runaway global warming. This was 1960. I went back to Scripps in 2012 and asked about this. Older retired scientists agreed and were worried, but younger ones refused to speculate. I felt that they were afraid of the politics and losing grants. Is this a big issue? I can't quite read the last part, but do you think there is an issue?
No, I don't think there is. In fact, I think it's almost the other way that if you sort of say, oh, well, this is interesting and scientifically interesting, but it's not that big a deal for humans, it's harder to get funded, whereas I think if something posed a real risk to humans, it would actually be easier to fund. And I guess the last time I really thought seriously about this problem was when I worked with Jim Casting many years ago when I was a postdoc at Penn State. And at that time the view was that moist atmospheres would condense out, that if you basically evaporated the ocean, that it would condense back out. But that if you go like another billion or 2 years into the future when the sun is hotter, then the tropopause gets hotter, which is the cold layer between the stratosphere and the lower atmosphere. And that allows more water vapor to pass in the stratosphere. It photodissociates and you lose the hydrogen into space and the ocean becomes a dry orb. I mean, we lose, but that's probably 1 to 2 billion years in the future.
Yeah. So there have been a couple questions.
I knew something about that one.
Yeah, there have been a couple questions on this. Have there been any long-range studies on the health effects of different types of geoengineering programs?
There's answer is not much. There's one study that I saw talk of only, so that's my level of expertise. I saw one 20-minute talk, but that it was on the particulate, first of all, there's a whole range of particulates, but and actually Alan Robach's done some modeling work of this, but the, if you think of the Chinese power plants, those sulfur emissions are right where people live and they're breathing that all the time. If those same aerosols were put in the stratosphere, most of them would come down far from where people live and in a much more dilute form. And so I think that the estimates are that the health impacts of a stratospherically injected sulfate particle is like 1/30th of what it would be if it were, come out of a power plant. That one falls in the category of somebody I know told me that, and I'm repeating it.
Yeah. Do you have any comments on the misinterpretation of the new Fayed paper?
Can I say that I haven't been reading, keeping up on the literature, and somebody should tell me what that one is? If they told me what it is, I would maybe.
Okay, I thought you might know. So
no.
since
Do you know
told you I know, now I don't know.
Okay, good.
So,
see?
this I do know. Okay.
You do know? Oh,
this I do know. The next question I do know. Well, I know enough to know that you might know the answer. What parallels, if any, exist between possible Earth futures and what we think may have produced the Permian die-off?
Well, yeah, I mean, the old story of the Permian so I don't know. I mean, this is one of these cases where I guess the one who I know who deals with Permian die-off is Jonathan Payne at Stanford. And, as far as I could tell, I mean, it looks like at the same time as the Siberian traps, but actually getting the causal links to me is not well understood. So I don't really know what caused the Permian die-off, so I don't know.
Yeah, talk of massive acidification.
Yeah, but then there's some repeated events, and it's hard to maintain acidification for so long a time as it's over many millions of years. So I don't really know, but let me just say something I sort of think I know, and that that's relevant. And that, if you think it's acidification, I don't see acidification. I see it as an existential threat to some types of ecosystems, such as coral ecosystems, but basically in the ocean, wherever there's light and nutrients, something will grow and something will eat that. And so I think it's a biodiversity and an ecosystem loss thing, but there's no threat to net primary productivity, whereas I think in Permian there's probably a die-off of net primary productivity.
Yeah, I mean, so for those not in the know about the Permian, the estimate is 95% of species died.
I actually think in those prolonged extinction events that more attention needs to be given to possible poisoning of the ocean, and that maybe poisoning might be a better explanation for how prolonged these die-offs are.
There are two questions that really come back to the coral reef coral reefs. So, what is the future for coral reefs, sort of best and worst case scenario? And then, related question: do you see potential for assisted migration for corals?
So, if we don't curtail our emissions quite rapidly, like more rapidly than any politician is currently considering, that I think by mid-century, pretty much every coral reef in the world will be unsustainable, which doesn't mean that it will disappear right away, but it's much easier to occupy some geographic territory than to come into new territory. And so if there's a storm or maybe a disease or some starfish epidemic or some pollution event that causes, or bleaching events from high temperature that causes the reef to kind of die off, and if under a more natural condition they would come back, I think by mid-century they're going to not be coming back. And the other thing is that reefs are a balance between calcification or reef skeletal growth, and there's all these parrotfish and things chewing on the reef and causing it to go away. And by mid-century, I think under current conditions, basically all the reefs will be in a sort of state of net erosion. So I think basically coral reefs will be gone. And after again, paleoclimate is an important window to understand. In past, say the end Cretaceous extinction, it took the better part of 1 million years for reefs to come back at the end of the extinction event. So it could be many hundreds of thousands of years. So that's the sort of worst case. The best case is So do I want the best case? Yeah, the best case is that we stop emitting CO2 and things don't get much worse than they are today and start getting better. The moving corals around is good for thermal stress. So if you take a warm water coral and put it into colder water, that maybe thermally it will do better. I mean, you know, heat stress when it move it to cold water, but unfortunately the way the chemistry goes, the colder waters tend to be more acidic than the warmer waters, and so from the ocean acidification point it's worse. And so I'm not overly optimistic about it, but it's worth a try in some cases.
So there's a couple of related questions. So let me just go through. You'll see the links. If there was no if there was no pushback from politicians and policymakers and climate change deniers, do you think that there are scientific solutions to climate change? So you talked about a solution, or at least monitoring an effect of acidification. So let me just, so for example, reversing ocean acidification, warming the atmosphere, et cetera. And then, another related question, are we qualified to manage Earth systems? Is stewardship foolish hubris?
So, we did a paper in 2010 in Science where we looked at, what if we never built another CO2 emitting device? So we never built anything else with a smokestack or tailpipe. But then allowed the existing infrastructure just to live out its normal life and retire it. And the atmospheric CO2 concentration just gets a few tens of parts per million, so just a small amount more higher than today's. And so most of the warming that's expected this century will come from things that we haven't built yet. And we certainly have a wide suite of technologies that can provide us energy without releasing greenhouse gases to the atmosphere, but they cost more money. But economists estimate that it costs a couple of percent more than, it would cost us a couple of percent of GDP to do that. And our medical costs are getting close to 20% of GDP. I forget what it is, 18%. Military is getting close to 10% of GDP, by maybe, 7, 8, 9%. And so, both of those things together are well over a quarter of our economy, and the solving the climate problem would be a problem taking an order of magnitude fewer resources than that. And so it would cost money, but we could do it, and it would be smaller than other things we're currently wasting money on.
Couple more. Yesterday an article appeared in Nature Climate Change, confirming, it says, a global warming hiatus between 1997 and 2014. That was previously claimed to be untrue by some other scientists. So I guess I'm gonna generalize this. Do you care whether there was or wasn't a climate change hiatus?
Yeah, meteorologists traditionally have used 30-year periods. So if you want to say, what's the climate of an area, meteorologists have typically taken a 30-year record as kind of being the minimum to get a sense of what the climate is of an area. And one person's noise is another person's signal, so everything has some causal explanation. And, I'm sure that scientists will come to understand the slowdown in warming over that period of time in greater detail, but nothing causes me to think, that carbon dioxide is not a greenhouse gas or something like that. And and then I think the fact that last year was the hottest year on record, and this year is likely to be. Also, last year there was the strongest hurricane in the northern hemisphere. Went into Mexico. Just last week was the strongest hurricane ever in the southern hemisphere. My brother happens to live in Fiji, and it went right over his house and destroyed the village he's living in. And and when you have the strongest, in the space of a few months, the strongest northern hemisphere hurricane and the strongest southern hemisphere hurricane, for the first time in history, a hurricane went into Yemen in the Arabian Peninsula. When things are happening, and it's not all natural variability.
This gets to more of the social science side. Would mass education of the nation's youth about socialism Help create a foundation. I didn't notice the socialist part. Help create a foundation towards greater success in overcoming climate policy barriers. And of course, this would be a grassroots movement, such as according to Naomi Klein.
First, I'm a big believer in education. I think in order for democracy to work, you need an educated population. And I think one of the reasons that politics is the way that it is in this country is that people don't have any real understanding of the issues. And so they're responding to these tribal impulses rather than, having some kind of fact-based policy decisions. And should people learn about socialism? Yeah, but I think they should probably also learn about fascism and capitalism and everything else too.
Yeah, these are, some of these are, well, what do you think about Edward Snowden?
I like Edward Snowden.
Yeah. A number of the others are pretty technical, and I think I'm going to let them go. I think I'm going to let it go there, and thank Ken again. Thanks a lot. I want to thank everyone for coming tonight. Climate conference starts tomorrow at 10 a.m. If you didn't get a program, you can get one now on the way out. And yeah, we hope to see you tomorrow. Thanks for coming.
Up and talk to him. I don't think I should go up and talk to him on what to say. Because the thing is, he's just going to...
Yeah, he avoided the whole geoengineering in this whole talk.
That's true.
Yeah, I think on purpose.
Actually, that's a good point.
Yeah. I think there is hope still.
Same driver who bought
Whatever there was, I could explain the data.
Hi there, how's it going? How's it going?
Remind me of your name. I'm
Patrick.
Patrick,
yeah. Are you going to discuss geoengineering at all?
No.
Not at all?
Especially not.
Why not?
Because I don't want to talk to you.
But I mean, you got my health paper. Are you not going to address that? The health impacts? You only talked about sulfates.
That was my question.
Sorry.
Yeah.
I didn't want to talk to you about it.
Are you coming tomorrow or no?
I have to talk to my wife.
Okay. Well, if I don't see you, it's great to see you.
When you took it off, I don't know if you pocket that feels
You're the panel tomorrow. Is it appropriate somehow?
Correct,
Hi, nice to see you. Nice to meet you.
He forgot my name.
Oh, I saw you on the RSVPs. I was hoping you'd make it.
Oh well.
They remember now.
Yeah. Well, like I said, there's forgetfulness seems to run in the Carnegie Institute. So yeah. Oh well. What can you do? Oh well. We had a good turnout though, I think. Yeah. More tomorrow.
Good job, Patrick.
Yeah. I should have heckled while he was like talking about Katrina and stuff.
I should have also when
Yeah.
we talked about Yemen's hurricane.
Yeah. Like said, oh, none of this is natural. Yeah, no.
Yeah. Did the hurricane hit strategic oil fields?
Oh yeah.
Of course it did.
Yeah, exactly.
He only talked about sulfates.
And sulfates, of course.
Yeah.
Of course.
He neglected to talk about aluminum nanoparticles and aluminum oxides.
Yeah, seems to be unaware completely.
Yeah.
Oh well, clearly be.
What was his quote? It's only 1/30th as toxic as coal-fired
Some
plants.
flannel, but he was talking about sulfates, which is just hogwash. Because that's not what we're finding in the rainwater.
And what did David Key say about sulfates? That they don't have the refractive.
They're ineffective. Yeah, they're the wrong shape. They coagulate, they fall out of the sky. Instead, you have to use nanoparticulate aluminum, barium, and strontium.
Correct.
And they're quite easy to deliver. And Ken was standing right beside him when he was talking about that in AAAS in 2010, I think it was. So yeah, it's
And that's what we're finding in the rainwater samples, right?
Yeah.
Yeah.
I gotta say though, I mean, to get one of these Carnegie gigs, go play in the Great Barrier Reef for 5 weeks a year, and for some,
So I'm here with Patrick Roddy and Ken Caldeira.
BFF. And if anything, I feel miffed. We're BFFs and he forgot who I was. Who are you again?
Yeah. All right. Great. Thanks, Patrick.
So, using Santa Cruz. Could have laid Central, but hey. All right.